And welcome to 19.3, where we're going to be dealing with the strengths of acids and bases. In this section, we're going to take a look at the fact that not all acids are of the same strength, neither are all bases. Alright, so let's go ahead and jump into acids here and see what we have in terms of varying strengths. Some acids are referred to as strong acids, and these are acids that fully ionize in water. Now, if that sounds familiar to a definition that you had before in terms of electrolytes, strong electrolytes are those that fully ionize in water. That's true because strong acids are in fact strong electrolytes. All right. In this case, they're only dealing with those strong electrolytes that are acids. For example, if we have a generic acid, and we'll just say HA, and we put that into water, and let's say that we have 100 molecules of HA. Once you put that into water, virtually all of them will turn into hydrogen ions and the anion. Alright, so you'll get 100 of these made, you'll get 100 of these made. As 100 of these split, you'll have none of those left. That's what strong acids do. Now, what acids are strong? Well, in fact, there are only 7 of them that you have to worry about. So let's go ahead and list those. You have sulfuric acid, nitric acid, and hydrochloric acid. Those are 3. Then you also have HBr, hydrobromic acid, HI, hydroiodic acid, HClO3, which is chloric, and HClO4, which is perchloric acids. Now I separated those 4 because these are the main 3. These are produced in mass quantities and are used in all sorts of industrial processes, where the other 4, though they're important, are not used nearly as much as the first 3. So make sure that you know those first 3 of the strong acids. If they are not one of those 7 strong acids where they fully ionize, they must be weak acids that only partially ionize in water. And so what do those look like? Well, if we give you an example, let's just say generically speaking, if we have an acid and let's say we started with 100 of those molecules, in fact only 1 of those would turn into hydrogen and the anion. You get 1 of these and 1 of these. In fact, 99 of them would stay on the left, and you would have an equilibrium situation where both the forward and the reverse reactions are happening at the same time, etc., etc. So only about 1% of these things actually dissociate. Now, what are some common weak acids? Well, acetic acid, which is in vinegar. Dilute acetic acid is vinegar. HC2H3O2. Phosphoric acid, which is used in many drain cleaners and other applications. Hypochlorous acid, which is found in bleach. And carbonic acid, which is actually a fictitious acid. You can't actually isolate H2CO3, but it behaves that way, and that's what would be in soda pop. Now, because this is in equilibrium, we can write out an equilibrium expression. So again, here's our equilibrium expression, same as above. If you wrote that out, you would say that K equals the hydrogen concentration times the anion concentration divided by the acid concentration, HA. And because this is specific to putting an acid in water, we call it the acid dissociation constant, and we call it Ka. Ka, just like Kw, is just like any other equilibrium constant K. You write it the same way. Products raised to their coefficients power divided by the reactants raised to their coefficients power. Leave out any solids or liquids. And that's what we've done here. Alright. Now, weak acids are going to have small Kas. Why? Because if they had large Kas, the reaction would lie far to the right and would be considered a strong acid. By definition, they have to have small Kas. But the larger the Ka is, even though it's small, the larger it is, the stronger the acid. So not all weak acids are the same. There are some very strong weak acids, and there are some very weak acids. The term strong versus weak only refers to how far to the right or to the left the equilibrium lies. It does not imply danger necessarily. If you have an incredibly dilute strong acid, it poses no danger. If you have a very concentrated weak acid, it could be very, very caustic. Okay? So this has nothing to do with the danger involved. It simply has to do with where the equilibrium lies. And the only thing I'm going to have you do in this chapter, I'm not going to actually have you calculate Kas and whatnot, since we've done equilibrium in a previous chapter. All I want you to be able to do is compare the strengths of weak acids. So for example, if I give you these 5 weak acids, can you put them in order of strength? Number 1 being the strongest and number 5 being the weakest. If you want to pause the podcast and try to do that, feel free. Alright, so to figure out what's the strongest weak acid, you simply have to look at the Kas and figure out which one is the largest. Well, you don't necessarily want to focus on the first term, you want to look at the exponents. 10 to the negative 2, that is the largest Ka. All these other ones are smaller. Now remember, this would have to be 0.056, while this one above it would be 0.0000043. So just remember, keep that in mind. And when you're dealing with negative exponents, you have to know how to interpret them. So since this is the largest Ka, this would have to be the strongest. The next largest would be the phosphoric acid. Now you have 2 of them that have 10 to the negative 5s. Those would be 3 and 4, but now which one is larger? Well, since they're both 10 to the negative 5, now you focus on the second term, and since the 6.3 is larger, that makes that whole term larger, so this would be the 3rd strongest, the 4th strongest, and then the carbonic acid would be the weakest acid, meaning the fact that it has the smallest Ka. Alright? So, in terms of strengths of acids, you need to first be able to recognize if it's strong versus weak. You have to memorize your strong acids. And then if you know that it's a weak acid, you should be able to put them in order of strength. In the next podcast, we're going to take a look at the strengths of bases. We'll see you next time.